Hi everyone, it's Mr. Hamilton here. This video is all about sequences and series. We're going to look at arithmetic sequences, geometric sequences, the sums of those sequences, and binomial expansion after we look at Pascal's triangle. This video is designed to be a complete overview of the sequences and series unit in the grade 11 math course. However, if you're in grade 10 or grade 12 or beyond, you'll find this helpful as many of the skills are transferable to other math courses as well. This question says the sixth term in an arithmetic sequence is 74 and the seventh term is 71. Find the 50th term. So the first thing we have to do is recognize this is an arithmetic sequence. An arithmetic sequence means that it's a type of sequence where you have some starting value and you are adding a difference to that every time. So we'll call that difference that we're adding a d value. So the second term has the d value added once, the third term has the d value added twice, and in the example that you see in front of you, we're adding 2 every time. So what that means is that the d value here is 2, and the a value, the starting value, is 1. So with those two things in mind, that's one example of an arithmetic sequence. Geometric sequences, on the other hand, are sequences that you start with a value. We're still going to start at, and we'll call it a, but then we're going to multiply by a value every time. We'll call that value that we're multiplying by r. So the second term is that starting value times r. The third term is that starting term times r twice, so r squared. So for example, I take 1, I multiply it by 2, I get 2. I multiply that by 2, I get 4. I multiply that by 2, I get 8, etc. So my r value there is 2, and my starting value is a equals 1. So this is an arithmetic sequence, and we're going to look at the general term now of that arithmetic sequence. The general term says that it's Tn, so that means what term number it is, and then it's a, the starting value, plus n minus 1 times d. Now that n is just the number term you have here. If that's applied to a geometric sequence, then we have a times r to the power of n minus 1. So now for the arithmetic, because that's the question that we have up above, let's focus in on that now and see how that one applies. So the first thing to keep in mind is that term 6 is equal to 74. We can write that in notation like shown, and term 7 is equal to 71. The difference between those terms, because they're subsequent terms, is this later term minus the previous term. So we could write it as term 7 minus term 6, so 71 minus 74. And so what that means is that we're subtracting 3 from one term to the next, all the way through the arithmetic sequence. So now we can go ahead and we can substitute the information from term 6 equals 74 and that d value into the equation, and the fact that we know everything except a means we can solve for a. So term 6 is equal to a plus 6 minus 1 times negative 3. Now that sixth term is 74, so we can also sub that in. And so it's a times 5 times negative 3. Well, that's just a minus 15, that's equal to 74. And so if we add 15 to both sides, we can solve that for a, and we get that a is equal to 89. And so from there, now we go ahead and we revisit the Tn equals a plus n minus 1 times d, but we can substitute in the a and the d value now. So the a is 89, and the d value is negative 3. So now I know I'm after the 50th term, so if I put n equals 50 into this equation, then I can go ahead and say 89 plus 50 minus 1 times negative 3. So that 50 minus 1 gives me 49, so it's 89 plus 49. And so really what we're doing is we're starting at that 89 term, and we're subtracting 3 49 times, which should make sense because every term that we go to after the first one goes down by 3. And so we get a final answer of negative 58. So we can conclude, therefore, the 50th term of this arithmetic sequence is going to be negative 58. If you had a geometric sequence, you would have done a very similar process. You could have taken the equation that you have there for the general term and subbed them in just the same way, but instead of adding or subtracting to rearrange the equation, you would have done some division. This question says, state whether or not the following sequence is geometric. If it is, state the general term and the recursive formula for the sequence. And it gives us the first 5 terms. So T1, term 2, 3, 4, and 5 labeled as such. So what we want to do with that is we want to go ahead and we want to divide every term by the previous term and look at that multiple. Because if it has a common multiple that's being multiplied by every time, then it's geometric. So term 2 divided by term 1 was negative 4. Term 3 divided by term 2 is also negative 4. And then if we divide term 4 divided by term 3, that again is negative 4. And then the last one we check, term 5 divided by term 4, we have to take the negative 768 and divide it by 192. And I get, again, negative 4. And so this is really helpful because it tells us, because that multiple is the same every time, therefore it is a geometric sequence. And that's always the case. Anytime we have a common multiple or a common factor between all the division statements like so, then it's going to be a geometric sequence. So therefore it is a geometric sequence since every term is multiplied by the same value to get the next value. Now, what is the same value? Well, in this particular case, it happens to be negative 4. So that is what we know as the R value that we'll look at in now the general term and the recursive formula. The general term is written for a geometric sequence like this. Tn is equal to a times r to the power of n minus 1. So the n minus 1 is done before applying r to the power of that. So Tn in this case is equal to the starting value a, which is negative 3, times negative 4 to the power of n minus 1, because that r value, that common multiple, is negative 4. The recursive formula is written like so. We write it out as Tn is equal to r times the previous term, Tn minus 1. And so we can go ahead and we can say, well, this is negative 4 times the previous term. But we do need a condition here, and the condition is that we have to have a starting term. So we have to have a condition that T1 is equal to the initial term, and so that means that T1 here is equal to negative 3. So now if we were asked to find the 10th term, we're not asked to do that here, but just so you know how this would operate with this, we would do something like this. With the general term, you'd say negative 3 times negative 4 to the power of 10 minus 1. Now BEDMAS says you have to do the exponents first and apply that. So the 10 minus 1 is applied, and then the negative 4 to the power of 9. And once you get that, you multiply it by negative 3. And so the 10th term is actually quite a large number, which is 786,432. If you were to do that using the recursive formula, it would take you a lot longer to do that, because what's happening there is you would have to generate the second term, then you'd have to generate the third term just by substituting in the previous value every time in for the Tn minus 1 to get the next value that comes. Now that might not be useful for you, but for a computer program that does loops and does the same thing over and over again to get an answer, that's a really, really useful thing to be able to have. Determine the following: the sum of the first 5 terms of an arithmetic sequence with a first term of 3 and a common difference of 7. So the first one is an arithmetic sequence. So let's look at what an arithmetic sequence is. Well, it's something that we know it starts with 3 and then the common difference of 7. So the next term is going to be adding 7. The term after that is going to be adding 7 twice to the original term of 3. The term after that is adding 7 3 times. And then the final term, the 5th term, is going to add 7 4 times to that original 3. So we could calculate this fairly easily without any equations or anything, because it's just the first 5 terms. So it's 3 plus 10 plus 17 plus 24 plus 31. We add 7 every time and we generate those 5 terms. Adding them together gives us a total of 85. Now that seems all simple, but what if I was to ask you for the first 100 terms of that arithmetic sequence? That's going to take you a lot longer to do. So if there were more than 5 terms, what should we do? So let's have a look at that now. The first thing to notice is that we could set up a general equation for this. It's really saying the a term, that's the starting term, plus the a plus the difference term. The third term is a plus twice the difference term, all the way to the very end when we have a plus the difference term times the n minus 1. So if I have 50 terms, I have 49 difference values I've added to that, for example. So if I write that out like so, that's a sum of a sequence like so. But then if I write that same thing backwards below it, so I'm starting with a plus n minus 1 times d, and then I go to the next term would be n minus 2 times d, the next term would be n minus 3 times d added to the a. If I do that same thing and I add all those together and I line them all up, if I add vertically, and I add the a plus n minus 1 times d, the first 2 terms there, I get 2a plus n minus 1 times d. If I do that with the next 2 sets of brackets that are lined up on top of each other, I get the 2a plus n minus 1 times d again. In fact, I get it every single time I add up these numbers together. And so what we could say is, in general, we have this 2a plus n minus 1 times d. And so we have n of those, so we have n times 2a plus n minus 1 times d. But the problem is that we've actually counted this twice, because we've set it out in one order and then we've done it in the reverse order below. We've counted it twice. So in order to account for that, we have to divide it by 2. And so that entire sum is going to be that equation, because now we've divided that by 2. So let's use that equation to calculate the sum of the first 5 terms of the arithmetic sequence now, instead of just laying out all the numbers. So we go ahead and we substitute n equals 5. We substitute in as well that a equals 3, so it's 5 times 2 times 3, plus n minus 1, well, n is 5, so 5 minus 1 times that difference of 7. So working from inside to outside in the brackets, and then using BEDMAS, we get an answer for the sum of the first 5 terms of 85, just as we did the other way. So now let's move on to look at the second part of this question that said the sum of the series from 1/2 minus 3 plus 18 minus something all the way to minus 3,888. The thing to notice here is that we're multiplying each term by -6. And so if we're multiplying each term by -6, that actually means it's a geometric series. And so because it's a geometric series, what we're going to do is we're going to use a formula that we have for that. It's not quite as obvious to derive as the last one. So I'm just going to show that to you, because this is a very well accepted formula that is used whenever we calculate the sum of geometric series. So it's n plus 1. So what that means is it's the term past the last term. So if the last term is negative 3,888, that means that n plus 1 is that times -6, which gives me in this case a value of 23,328. So the n plus 1 is that. We subtract the starting term of 1/2, and we divide that by r minus 1. Now r is -6, subtract 1, and you'll notice that this is Sn. We don't know how many terms are in the series, but we do know what the sum is despite that. So we go ahead and we simplify the numerator, we simplify the denominator, we divide those two things, and what we get is a final answer of negative 3,332.5. Now the interesting thing here, as I already said, we have no idea how many terms are in there, but the other interesting thing is that sum is actually smaller than the last term. And the reason for that is because the sign is switching on every term. So the sum is smaller than the biggest term in the series. Expanding and simplifying binomials is really tricky for a lot of people, but I'm here to show you just how simple that can be. We're going to look at 2x minus 3 to the power of 5 and how to expand that using Pascal's triangle. Pascal's triangle is all about the number of ways you have to go down on diagonals from a top point. There's one way to get to the second row, but if you go to this next row, you can go from the left or from the right, and so there's 2 ways to get there to the middle. If you go to the row below that, there's one way to get to the far left, but then if you look at this next point, there's 1 way to the left and 2 to the right, and so those add together to give you 3. And if you continue that pattern on and on and on, what you get are the following rows. Now the interesting thing here is that these actually correspond to the coefficients of whatever you're trying to expand as a binomial. So what we're going to do here is we're going to look at this. If you have an exponent of 1, then your coefficients will be 1 and 1. If you have exponent of 2, your coefficients are 1, 2, and 1, all the way down to 5. And our coefficients are going to be 1, 5, 10, and then 10, 5, 1. But we're only going to look at the first 3 terms. And this pattern that we see is going to continue for the other 3 terms that follow. So we go ahead and we write the coefficients 1, 5, 10. And we are going to add these all together because they're all distinct terms in this binomial expansion. Now we look at the first term in the binomial. It's 2x. We're going to start by raising that to the power that's on the binomial. It's 5. And then every subsequent term is going to be 1 degree less. So to the power of 4, then to the power of 3. And by the time you're at your last term, it'll be to the power of 0. Now the other term in the binomial, the -3 here, we're going to start that in the opposite direction. So we're going to start that at a power of 0 and count up. 2x counted down, the -3 counts up from 0. And so we then go ahead and we now have our 3 terms that we can expand and simplify. So 2x to the power of 5 is 32x to the 5th, and negative 3, anything to the power of 0, is 1. And then we are going to expand out the 2x to the 4th, and that's going to give me 16x to the 4. And then the 2x cubed gives me 8x cubed. And then the negative 3 squared is 9. So if we continue going now, 32x to the 5 times 1 is just 32x to the 5. And now what we'll notice is the sign changes here because we have one negative. So this gives me minus, and you multiply 5 times 16 times 3, you get 240x to the 4th. And then the next term has all positives, so it's positive or plus 720x cubed, and the next term would be minus again. The sign of the coefficient ends up changing every single time. Now remember, the coefficients we put in originally were 1, 5, and 10. But when we actually apply the parts of the binomial, that can determine if we have a positive or we have negatives as we go along. So it doesn't end up being 1, 5, and 10 at the end, but that factors into giving us those final numbers once we've simplified everything out.